Hello everyone, my name is Nitya Nand Gosvami. I am an assistant professor in the Department of Material Science and Engineering at Indian Institute of Technology, Delhi. Today I'm going to talk about how AFM can be used in liquids for studying tribology, which is friction wear, and some of the more recent work which I'm going to share with you is on tribochemical reactions, which uh, occurs during sliding at the interface uh, between the two sliding surfaces. So before I move further, I would like to thank NanoSurf for giving me this wonderful opportunity to share some of my research work with you. So before I start, first thing I would like to do is to say briefly about tribology. So tribology is the science and engineering of interacting surfaces in relative motion, where we are particularly interested in energy and material loss due to friction and wear, and also we try to minimize these losses uh, via lubrication. Providing lubrication, it can be solid based lubrication or liquid based lubrication, and it's a very important field, and also it spans across all length scales, ranging from understanding natural phenomena such as earthquakes, where friction between tectonic plates uh, gives rise to earthquakes, uh, and engineering machineries, automotive engines, hard disks. They all have severe tribological problems which lead to failures, and also it results in energy loss, as well as uh, reliability of the components are affected due to these tribological issues. Tribology is also going to be important for futuristic devices such as MEMS or nanoscale uh, 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 applications where sliding or interacting surfaces are involved. So it is very important to address and understand the fundamentals of friction, wear, and lubrication in order to improve the safety, efficiency, and reliability of these uh, engineering components. And in terms of economic losses, if you can sum up the total losses every year due to tribological problems, it is quite a significant amount of GDP of any industrialized country, which is lost every year. And the primary reason why we are not able to minimize these losses further is due to a severe lack of understanding in terms of fundamentals of friction, wear, and lubrication. So, what makes friction, wear, and lubrication uh, hard to understand fundamentally is the complexity of the sliding interface. So, if you consider two interacting surfaces, the interface is where these surfaces touch each other is extremely complex. The surfaces are rough and they have large number of asperities, and these asperities are of different sizes, size and shapes. And when these asperities touch each other, then these surfaces experience friction and wear, and that's where we have to minimize these friction and wear related losses and providing lubrication. So when these interactions happen, these asperities press against each other. There is a normal force, as well as there is a shear between these two surfaces when there is a relative motion, which results in several processes happening at the same time. And these processes happen because these asperities are directly in contact with each other. And in addition to that, there could be apart from you know deformation of these asperities, there could be adhesion between these asperities, there could be material wear when shearing happens, and also there could be chemical reactions, particularly in presence of reactive environment, or these surfaces can also bond to each other or weld to each other if they are reactive. So the question is how to really understand the fundamentals of these interactions is to have a technique which allows us to look at these asperity level interactions. And AFM is one such tool which has the potential to address this because it provides us a very well defined contact where you have a single asperity contacting against a variety of materials which can be studied in this technique. In variety of environment, you can use all sorts of lubricants, for example, and these lubricants can have different chemistry, and you can study these sliding interactions under those conditions, and also you can have control over temperature as well. So the idea of using this technique is to go from empirical macro scale approach all the way to understand asperity level interaction, which is the fundamental uh, of these macro scale interaction, that the crux lies in the asperity level interactions. So if you look at the transmission electron image microscopy image of an AFM tip, it does look like a single asperity, and it provides us a single point contact which can be investigated to understand friction wear with very high nanometer spatial resolution. So one question we try to address using this technique is studying a lubricant which has an additive which is used for car engines. For example, uh, automotive engine oils contains this ZDDP molecule, and this molecule has been studied for decades, but it's not fully understood how it works, how it reduces wear between the sliding components. And but it is well understood that when this uh, molecule is added to the lubricant, it goes at the sliding interface with the lubricant, and that results in reaction of this molecule at the interface. And what has been observed is that at the sliding interface, some layer, a tightly bound layer is seen, which protects the surfaces. So it acts as a protective layer. And what has been hypothesized is that due to high contact pressure at these small sharp asperities touching each other uh, at elevated temperatures, and due to shear, these some kind of reaction happens in presence of these molecules which results in these films. But there's no direct evidence of how these films grow and what parameters govern the growth of these films, because of the complexity of these macro scale interfaces which have uh, been the which uh, has been very difficult to interpret in terms of understanding the local interactions. So what typically people do to look at these lubricants interaction with this metal surfaces is use tribometer tests, where they can use a metallic ball against a metallic surface. And what they have observed, whenever ZDDP is added to the lubricant, some uh, film starts to develop in presence of ZDDP. And as the time progresses, this film becomes more dense and thicker, and that results in anti-wear properties, because now metal-metal contact is prevented due to formation of this protective layer. But so far there was no evidence of uh, how these films form, exactly what parameters are important for the growth of this film. So we took up this approach based on AFM in liquids, and we conducted an in situ experiment. So we As I've shown this picture earlier, we have a AFM based setup which has a fluid cell where we can use a lubricant and use ZDDP in 1 weight percent standard concentration, which has been used in macroscale experiments. And we can use a steel substrate or iron coated silicon surface, which was initially used in our experiments, but later on we moved on to steel as well. And we used a silicon cantilever which is coated with diamond like carbon to provide a high wear resistance to the sharp tip, otherwise it will wear very quickly under high contact pressures. And then we did experiments at variety of forces, variety of temperatures, to look at what happens in this kind of environment. So here is the schematic of the experiment. So we select a very small region of interest on the sample surface, and we slide the tip at different loads, which will vary the contact pressure between the tip and the sample. And then we do these experiments with different temperatures at different length scale in terms of sliding time, and monitor what happens to the surface. And we were successful in conducting an experiment where we found out condition where at certain critical pressure we saw that when sliding happens at high certain critical pressure above certain values, the film starts to develop. And then we image this film by applying low pressure and take a larger area image so that we don't form the film outside this region of interest. So as you can see, we have stitched several images together to show you how the film growth is progressing with sliding time, only in the region where high contact pressure was applied. So it's a highly controlled experiment performed at very localized region of the sample, and we first time very clearly showed that this film develops only in a region where pressure above certain critical value was applied. Uh, and then we did very systematic study as a function of contact force, which will vary the contact pressure. So in terms of increasing pressure, we saw that film growth for a given sliding time is thicker for higher contact pressure. So as the pressure is increasing, film thickness is also increasing for a fixed sliding time. And of course you start to see wear or deformation of the film when the pressure becomes too large. So in order to understand how this pressure is affecting the reaction, and another parameter is the temperature, we saw that this reaction did not happen at room temperature. So how to take into account these parameters? So we uh, try to analyze it in terms of a simple chemical reaction. It's a single barrier Arrhenius type reaction rate theory. So we assume that growth rate of the film is uh, exponentially dependent on temperature based on this Arrhenius reaction rate theory. But we saw clearly an evidence of stress applied at the tip sample contact. So we have to take into account stress or contact pressure as well. And the idea behind how we can incorporate stress in this equation is by assuming that energy barrier is reduced as stress increases, which is evident in our experiment that when we increase contact pressure, we see that reaction is happening at a faster rate. So this is something very simple model we used where we took into account the stress multiplied by activation volume, which is the reduction in the energy barrier due to application of stress. So we modify this equation by taking into account the stress or contact pressure multiplied by activation volume, which will reduce the energy barrier. So this equation 1 will convert into this final equation where we have temperature as well as stress taken into account. So then we did systematic study where we varied the contact pressure and we looked at the growth rate of the film in terms of volume of the film growth uh, observed per unit time. And we see that very nice fit to the data uh, up to certain value of stress. So we see that at very low stress values or contact pressure values, the growth rate is very small and it exponentially increases with increase in contact pressure. But what happens beyond this point, uh, that this model doesn't fit, and the reason for that was clear to us when we looked at the AFM images of these films. So we saw that in this region where the data is fitting well to this equation, we see that uh, film is not damaged or it's not wearing away. So whatever reaction is happening, the film is building up, getting thicker and thicker. But after that, the film thickness became almost constant, or the growth rate saturated. And this is evident in the image. If you look at this image at higher stress, you see the film has deformed quite significantly. You can see some kind of a shearing of the film has happened. So significant wear of the film starts and then growth rate will saturate. So we managed to get some reasonable numbers from this. The activation volume came out to be of the order of size of atomic dimension, and energy barrier is also indicating some kind of chemical bonding is happening between this molecule and the substrate. So of course it's not telling us exactly what reaction is happening, but it is providing us a clear evidence that it's an activated reaction which is assisted by contact pressure or stress applied. So in order to further confirm this activated model, we did a separate experiment where we maintained the stress as constant and varied only the temperature. So in that situation, we again got data which showed that growth rate is increasing with temperature in exponential manner. And again, the fit looks reasonably good. And we got very similar values of energy barrier, which suggests that by doing independent stress variation and temperature variation experiments, we confirm that it can be described as a chemical reaction which is driven by stress and temperature. So this was the first time ZDDP molecule, which is actually an automotive uh, lubricant additive, has been studied at this length scale, and that was possible because of the availability of tools such as an AFM which can work in those kind of environments. So this was very encouraging and it opened up a lot of new avenues for us to look at molecules or lubricant additives which are relevant for macro scale tribological applications. So we of course confirmed the formation of this film and showed that this chemically this film is derived from ZDDP because we have the elements which are present in this molecule, phosphorus, sulfur and zinc, and that confirms that this chemical reaction has happened in the region where sliding has taken place. So some, of course, several questions were asked when we did this work, that how this is relevant for multi-aspirity contact where you have more complex interface. Will it be identical in those situations, or how do we translate our results to higher length scales in terms of large contact size? And also our tip was diamond coated silicon, so how do we relate this to steel on steel contact, for example? So we modified our AFM setup. Instead of using a sharp silicon with diamond coated tip, we moved on to a spherical probe, which is a microsphere of 30 to 50 micrometer diameter, and it can be made of any material of which is available um, uh, in the market, such as silica sphere, it can be alumina sphere, it can be steel sphere, which are also available. So we found a supplier of steel microsphere, and we glued a sphere of steel here, which has some surface roughness as well. So we generated some kind of a microscopic multi-aspirity contact to visualize how this reaction is going to change when you have such difference in contact geometry. And we did an experiment on a steel substrate, so steel on steel in the same lubricant. And this is an SEM image of one such steel microsphere attached cantilever. So we found that actually when we did sliding, we could again simultaneously record the image of the sliding interface, and this is a polished surface. You can see the polishing marks, and you can see that film is growing, of course, preferentially on the sharp scratch on the surface because there are stress concentrations, and film is growing uniformly. It forms island like patchy topography, which we have seen previously as well in single aspirity experiment. And we found that similar to the single aspirity experiment, this film has formed only at elevated temperatures. And one more advantage of using this microsphere against a flat surface was that we see that friction force is proportional to normal load, and from there we can calculate the coefficient of friction, which makes this tool more similar to a tribometer, which people use for macro scale friction wear and lubrication experiments. So this the major advantage is that you can also have variety of probe material which can be used in form of microsphere attached to the commercial AFM cantilevers, and then you can study variety of tribo pairs. So we found that the film growth appeared to be very similar to what we have seen in single aspirity contact. Film growth happens at, of course, if we press harder, we see that film growth is faster, and also it happens particularly at faster at elevated temperature. So we could manage to do experiments in very controlled condition with very controlled geometry, which allows us to understand in better way how these molecules are reacting at the sliding interface. And in a multi-phase system, it can become very important because you want to see how these local reactions are happening if you have heterogeneity on the surface and so on, which I will demonstrate uh, as well. So in terms of heterogeneity and looking at more realistic systems, we have started doing now experiments on different alloys. And one such example is aluminum silicon alloys, which is heavily used in automotive engine block manufacturing. And this alloy primarily has two phases, which is aluminum matrix, which is the light color region, and silicon phase. Of course, it has some intermetallics, iron-rich intermetallics as well, but those are not significant fraction of the microstructure. Majority is silicon phase as well as the aluminum matrix, which is very soft aluminum region around hard silicon particles. So my student Prashant, he looked at interaction of ZDTP on these surfaces, and we uh, looked at how these films develop on different regions of the surface, which has silicon and aluminum matrix. So before I share the results, I will show what people have seen on these alloys in terms of formation of these films. Uh, so it has been observed that in macro scale experiments that mostly silicon phase is where the tribofilm develops, and GGTP forms nice thick protective layer on silicon phase, but aluminum matrix doesn't seem to support these films. But the reason is not very clear because of the complexity of the macro scale sliding interface. A lot of wear is generated in macro scale experiment. Then there is a lot of mechanical mixing. So a lot of damage happens to the interface, which makes it hard to interpret the results. There's another set of results which shows similar observation that silicon is where tribofilms are developing, whereas there is no tribofilm on the aluminum matrix, which is the softer region around silicon. So we did this experiment in a more controlled manner where we selected a region of silicon and aluminum matrix around it and did a simultaneous sliding. So when we do simultaneous sliding, actually we were puzzled to see a contradictory result where we see tribofilm developing on both aluminum as well as silicon face. Uh, then we analyze these tribofilms in more detail, and here is the final AFM image. So this is the silicon phase on which tribofilm has developed. You can see the islands of the tribofilm, and the aluminum matrix around it also has these films. But there was a clear difference in when we look at the topography and height of these tribofilms. We saw that tribofilms were thicker on silicon, uh, around 70 nanometer on silicon, with respect to aluminum where they were around 40 to 50 nanometers. And also the roughness of the tribofilm on silicon phase is very different compared to aluminum, where you see that islands, there is more gap between the islands of the tribofilm, so it's more patchy compared to silicon where there's more dense film. And again we could relate it to the stresses because silicon is a much harder phase compared to aluminum. So the contact pressure for a given load at which we are sliding, the contact pressure on silicon will be much higher. That will result in uh, uh, faster rate of reaction, and that will grow a thicker film. That's what we believe based on our observation we had earlier on ferrous substrate where stress had shown strong relation to the tribofilm growth rate, and on aluminum, which is a softer matrix, stresses are significantly lower, uh, and that will result in thinner film. We could also chemically characterize this film simply looking at the elements present, and we see that there is higher concentration of these uh, phosphorus and sulfur where film is forming on silicon. Of course, it's denser and thicker film, so that is expected. Another interesting observation we made was when we are sliding uh, far away from the silicon, purely in the aluminum matrix, we see that film did not develop. We see continuous wear of aluminum. Uh, so we thought that it could be due to the fact that silicon is somehow affecting the mechanical property of the neighboring aluminum matrix with respect to a region which is away from the precipitate. But we did nano indentation and we see that there's not much mechanical property variation in aluminum matrix closer to the precipitate or away from the precipitate. So it has to do with something else, which can be related to small chemical changes in the substrate, but we have not yet fully resolved that, and we are still working on it. We also see that friction coefficient now we can measure because we are using a microspherical probe, ball and disc kind of tribometer type of setup, which we have now uh, started using uh, by attaching a microsphere to the AFM cantilever. So these friction coefficients also correlate very well to this friction and wear observation. So if you see, the coefficient of friction on aluminium is significantly lower when there is no wear of aluminium and there is no uh, damage to the surface. Uh, of course, it's higher on silicon, and we believe that higher friction on silicon is because ZDTP film increases friction, and this film is quite thick on silicon compared to aluminum, so that results in higher friction on silicon, whereas in the beginning there was not that much of difference, but as the film thickens there is more friction on silicon due to thicker tribofilm, whereas friction coefficient shoots up quite strongly when there is wear of aluminum matrix. So very nicely we can see that as soon as wear starts, how friction coefficient uh, becomes very large, and very locally we can study these differences by using an AFM. Uh, Apart from aluminum alloys, we are also interested in magnesium alloys. So my student Deepak, who has done some work on how these reactions happen on magnesium surfaces, magnesium alloy, which is AZ91 aluminum zinc alloy. So in this alloy, we have either cast alloy, which has large precipitates, or we can age uh, harden these alloys, and that is done to improve their mechanical properties, but age hardening results in finer precipitates. So how the microstructure affects the film growth was investigated in this work, and we found that ZDDP forms very nice tribofilm on large precipitates. So this is a flat surface of a large precipitate, Mg17Al12 precipitate, and around 40-50 nanometer thick film has been observed. Whereas magnesium does not support tribofilm formation, and we always see wear of magnesium matrix. So ZDDP is a very poor anti-wear additive for magnesium alloys because we could never see ZDDP forming a film on magnesium either close to the precipitate or away from the precipitate. We always see wear of the magnesium matrix. Of course, on the precipitate, we characterize the film and we confirm that these films are coming from ZDDP derived species due to presence of zinc, phosphorus, and sulfur. Whereas on matrix, we didn't see any such signals. Then we conducted an experiment on fine precipitate, which is the age-hardened alloy, and to our surprise, we could not see any film developed on this surface where the wear is also very small. So despite wear not happening to that extent, uh, particularly precipitates do not wear easily in an AFM sliding experiment. Both type of fine precipitate did not show any tribofilm, and the reason we believe is because of the corrugation of the surface due to these precipitates. So if you see, the surface is highly corrugated, and that will result, if the probe is sliding over such sharp features, there will be large stress variation and also stress concentration. And we have seen in the previous first experiment where I showed wear of tribofilm at elevated stresses, that is probably what is happening here, is that these stress concentration and stress variations are not allowing tribofilm to develop on the surface, and this corrugated surface prevents smooth or stable sliding of the probe, which is required for shear of these molecules so that they can react at the interface. Uh, we also saw some interesting wear behavior of these fine precipitate containing regions. So what we see that we tracked wear around a single precipitate, and we see that the precipitate actually do not wear as a function of, we did sliding tests at different loads. We can continuously slide and then we change the load and then slide again. So multiple sliding experiment conducted in a single region, we see that precipitate has not worn at all, whereas the matrix is continuously getting worn out as a function of time. So some wear is happening despite these precipitates are not wearing at all. So that it has a bearing on friction values, because if you see the data, friction force data here as a function of sliding time, so the fine precipitate regions, there is very gradual wear of the matrix around it, but pure matrix of magnesium wears completely, so there's the friction is maximum, and large precipitate where there's anti-wear film forming and there's no wear at all because there's no matrix, which is softer and preferentially wears. So there we see the friction is very low, and GDDP film growth as a function of time shows a very interesting feature on this large precipitate, where we see a dip in the friction, quite strong dip, followed by, as the film thickens, friction increases and then it's sort of levels off, and then there's some fluctuation, which we have not seen on ferrous substrate or aluminum substrate, but it was unique to these magnesium alloys. Another study we conducted on magnesium alloy is to use, now since we found that GDDP is not an effective anti-wear additive, we found that in literature macro scale studies have reported amide based molecules to be uh, reacting well with magnesium and forming some kind of a protective layer. But of course, detailed study at local microstructure or microscopic length scale was not been carried out. So we took up this AFM based approach, and then we again looked at uh, purely magnesium matrix in an as cast alloy, and we can clearly see that film has developed on magnesium alloy matrix, which is much softer, and it was wearing in case of ZDDP containing lubricant. But here we see acrylamide has formed a nice tribofilm. Of course, this tribofilm is only few nanometer thick, which is much thinner than GDDP films on the precipitate region. But in GDDP, there's no film develops on the matrix. And acrylamide based additive also showed very nice friction force variation with sliding time. As the film develops, friction increases quite sharply, but then as the film becomes thicker, the friction continuously drops, which is a good thing, because as the film gets thicker, friction reduces, so overall frictional losses will also reduce with sliding time. And on large precipitate, we saw the film is much thicker, and again we can see that harder phase is giving rise to thicker film. So stress is always helping uh, increase the reaction rate. And of course, as the film is thicker, we see sharper rise in friction and more higher friction than thinner film, and then sharper decrease in friction as a function of sliding time. So in comparison to ZDDP, acrylamide shows just the opposite behavior, where friction increases and then drops, whereas in case of GDP, friction first drops on the precipitate, and then it increases, and then it starts to hover around some values. But of course, GDP, this behavior is not seen on matrix or fine precipitate region, whereas acrylamide shows this behavior on matrix as well as on the large precipitates, which makes it very important additive for magnesium based alloys. And AFM allows us to systematically uh, study this differences between two different types of additives in very localized regions. But again, we did this study on a fine precipitate region, and we see that acrylamide does not form tribofilm, which suggests that these fine precipitates are not going to be good for lubricated systems where tribofilms are desired. So there some microstructure tuning is required to get this right precipitate size, which does not give you poor mechanical properties but also supports tribofilm growth. So now I will divert a bit and talk about another direction which we adopted from this kind of uh, work, where we are looking at sliding induced changes in the interface, looking at chemical reaction, and now we can utilize that for uh, making patterns on the surface, which we call it nanoscale triboprinting. So as this some of the results are shown here. So this was work was done in collaboration with Professor Harman Khare, who is now at University of Gonzaga. So we looked at how these reactions can be controlled, and we can, how well we can control in a way to pattern the surface, and that can have variety of applications for making channels or making devices. Um, in terms of application, there could be several potential applications in future. So we try to understand this patterning and try to see how well we can control this. So with ZDDP, we had a lot of experience. We could write these very nice patterns, and we could see that these patterns, the height of these patterns can be varied by changing the load, which increases the contact stress, and we see that contact stress activates the reaction, so we get thicker pattern, uh, whereas the thickness or width of the pattern does not change that much, only a few percent, whereas height of the pattern changes by factor of 3 by varying the load by factor of 3. And of course we see some asymmetry in the pattern as we slide at different angles because of the asymmetry of the contact itself. So that also matters. If the contact is symmetric, you will get symmetric pattern, otherwise you may contact shape will also affect the size and shape of the pattern. Um, then we try to extend this to other species such as nanoparticles, and we realize that with single asperity it's very hard to deposit nanoparticle or very hard to trap nanoparticles at the interface, because nanoparticles are of the same size as the size of the contact in a sharp tip. So we took again this approach of using a microsphere, and with a microsphere now you have a large contact area, and you can trap, if you have few nanometer size particles, you can easily trap multiple nanoparticles and probably write patterns, and that's exactly we did. This is one such cantilever used in this work, and then the idea is to trap multiple nanoparticles, and then under high contact pressure and shear you can deposit certain patterns. And this work was done in collaboration with Pixeligent, using zirconia nanoparticle. So here we see that we wrote line pattern, we drew rectangular pattern, and we uh, then characterized these patterns, and we found that these patterns are extremely robust. So this was 5 nanometer large zirconia nanoparticle, and after doing this sliding test, we see that these particles have completely sintered together, and there is a very sharp interface between the substrate, which is steel, and this zirconia film, which is deposited by sliding AFM probe, and these nanoparticles have fused together. And in the chemical characterization, we could not even find the capping agent which is used for dispersion of these particles, so they have sheared off due to this high stress conditions. And we see that the film has developed a highly crystalline structure. It's a polycrystalline film, so very dense. And also we did nano indentation and other mechanical property measurement, and we found that this film is very robust, as close to mechanical properties as bulk film, bulk zirconia. And then we also try to play around with mixing these nanoparticles with molecular reactive molecules such as ZDDP. So we can do either layer by layer patterning, or we can do kind of a composite coating where we mix nanoparticles and the reactive molecules together, and then we co-deposit these structures. So all sorts of patterning is possible by using this technique, where we have now the ability to control nanoscale chemical reactions in a very controlled manner, in a very well defined region of interest. And now we are going to try to look for application for these kind of coatings. So in conclusion, I have demonstrated AFM based approach uh, for liquid experiments, where we can have sliding of the probe which can trigger chemical reaction, and that reactions can be monitored in situ, and we can very systematically look at role of various parameters such as contact pressure or temperature, and we can uh, have these reactions to make novel structures, nanostructures or patterns, which can be utilized for a variety of applications. So with this, I would like to conclude and acknowledge all my previous collaborators where my work started, and my current affiliation where I'm continuing this work, my current collaborators, previous uh, companies with whom I have interacted closely to carry out some of this research. And mm, lastly, my research group at IIT Delhi. So I'm heading this nanotribology research group, uh, where several of these students were involved in the experiments I performed on, my group performed on aluminum alloys and magnesium alloys. So with this, I would like to thank you and be happy to answer any questions. Thank you.